In this exercise, we're going to use linear regression to predict the birth weight of babies. And this data is coming from this data set, which is published as a clinical journal. First, we're going to import the needed packages, pandas, numpy, as well as the linear regression model from scikit-learn, and some of the metrics we will use, such as the R-score metric. Next, I'm going to read the data, and I'm going to rename the columns here to make them just kind of shorter in names. The original data has longer columns names. So I just renamed the columns in this data to have just shorter names. So we have a bunch of variables here. We have the ID of the observation, which is identifying the baby. The baby low weight, which is a binary variable, either 0 or 1, depending on whether the baby has a low weight or not. This variable is useful when doing classifications, as we will see soon enough. However, in this exercise, we are interested in predicting the weight itself, which is this outcome variable, the last variable in our dataset. The remaining variables are some of the features we can use to predict the weight of the baby, including the age of the mother, weight of the mother, race, whether the mother smoked or not, had a premature labor, hypertension, irritability, number of doctor visits prior to giving birth. So let's take a look at these questions. First, we want to fit a linear regression model to predict baby weight using mom weight, premature labor, hypertension, and irritability. We want to print and interpret the model coefficients. And we want to make an assessment whether the model is making good prediction of baby weight. Next, we want to include the two variables, smoked and race. And those are two categorical variables into the data. And we want to see whether the model is doing better than the old one or not. So first, I'm going to pull from the data the feature matrix as well as the target array. So the feature matrix will be the variables that have been specified above: baby weight, mom weight, premature labor, hypertension, and finally irritability. Probably made a typo in one of these variables. It's the baby weight. Well, the baby weight we don't need here because this is the outcome array. So we actually just need the features: the mom weight, premature labor, hypertension, and irritability. Once again, I probably made a typo. Hypertension is not an index. Let's see. Well, it looks like the variable in the index is misspelled, so I'm going to do that again. And now we have our feature matrix here. Okay, the next step is to get the target array, and this one is going to be the baby weight. The next step is to create the linear regression model, and we need to specify any hyperparameters of that model. In my case, I'm just going to create a simple linear regression model, and I'm going to fit the intercept of the model as well. The next step is to fit the model to the data by passing the feature matrix and the target array. Now we want to print the intercept, the coefficient of the model, as well as the intercept. Okay, so let's take a look here. Now, so when we take a look at the intercept of the model, we need to look at these intercept in light of the variables we have. So an intercept of 4.4, it means any increase of the weight of the mom is, so an increase of 1 unit, which is, I'm assuming in this data is 1 gram or 1 pound, I'm not sure. We need to take a look at the units measurement in the data again. So I'm assuming this is in pound, but this one is in gram, so one has to take these units in kind of in relation. Each 1 pound increase in the mom weight is translated to 4.4 increase, 4.4 gram increase in the baby weight. The second one, which is premature labor, which is 1 or 0. 1 means a premature labor translates on average to a decrease of 106 grams in the baby weight. Hypertension, which is also a binary variable, it translates to a decrease of 655 grams in the baby weight. And the last one, which is irritability, translates to a decrease of 536 grams in the baby weight. The model intercept is the average baby weight given all of these variables are 0, which is again, it's not very useful in here because the mom weight of 0 doesn't make sense. The remaining variables, for instance, the premature labor, hypertension, irritability can be zeros, which is very fine, but a weight of 0 in the mom doesn't make sense here. But that's the average of the average expected baby weight when all of these variables are zeros. Next, we're going to look at the goodness of fit of the model. Does the model make a good prediction of baby weight? What I'm going to do, I'm going to fit my data. I'm going to do model.fit_x. Actually, model.predict_x. Okay. So next, I have the true y and the y fit. I can calculate the difference, and that will be the residuals of the model. Or I can use the function R2score, and I can provide the y and the y fit to that function. This is giving me an R square of 15%, which means that the model predicts 15% of the variance in the target variable, which is the baby weight. So this model is not great, it's just only predicting 15% of the variation. Understandably, this task is hard because there are so many variables that factor into the weight of the baby, including some of the variables in this data that we did not account for, but there are also a slew of other variables, clinical variables, genetic factors, environmental factors. There are so many things that factor into account. The next question is asking us to account for smoked and race in the model, and to determine whether the new model is better than the old one. Now, smoked and race are both string variables in the data frame, so we cannot include them prior to converting them to numerical variables. So there are two ways of converting to numerical variables. One way is to encode them to, for instance, encode each race with a number, or smoked with 1, non-smoked with 0. The other one is to create dummy variables, and each category becomes its own variable. The two choices are possible here. Usually with linear regression, we use dummy variables because they're easier to interpret than just encoding the variables with numbers. I'm going to use the function pd.getDummies, and this function by default will just convert any categorical variable to a bunch of dummy variables, a variable for each category. So this is useful here because the remaining variables are already numbers, integers. So I'm just going to call the function getDummies, and you can see here that we've got a variable for race black, race other, race white, and two variables encoding smoked, smoked non-smoker, and smoked smoker. I'm going to call this one data2 here. So the next step is to basically get the feature matrix again. So I'm going to copy this code. I'm going to add just the new variables to my X. Don't forget that this is data2, it's not data1 anymore. So in addition to these ones, let's take a look at the columns here so that we can look at what we want. We want to get actually data2 here. We want to get these variables, the race black, race other, race white. So I'm going to add these, as well as smoked non-smoker and smoked smoker to the feature matrix. Very often when those categories are exclusive, we end up just having one. Like for instance, we don't need to have smoker and non-smoker in the same feature matrix, because if the person is a smoker, the person is non-smoker. Actually, the mom. If the mom is a non-smoker, then the mom is not smoker, right? So this is completely determined by this one. So very often we end up leaving one of these and using the other one as a baseline. Again, adding it will not change any, anything related to the fitness of the model. So eventually will be the same, and this is something you can test on your own. What I'm going to do here, I'm going to just keep smoker using non-smoker as a baseline, and I'm going to leave out maybe white here. So I'm using white to be the baseline, comparing black and other to white as a baseline. So that's my X here. My white is going to be the same baby weight, so nothing changes here. And the remaining steps are going to remain the same. So I'm going to create the model here, and I'm going to fit X and Y. And I'm going to do the same. I'm going to take a look at the model coefficients here, model intercept, and I'm going to fit. Let's fit the data and then do the R-score, and then we will look at the results now. Last one. Okay, so let's take a look at what we have now. If you take a look at the coefficients, and again we have to compare them in relation to the variables. Mom weight, each increase in pound translates to 4 grams increase in baby weight. Premature labor is now associated with, on average, 53 gram decrease in baby weight. Hypertension is associated with 581 gram of decrease in baby weight. Irritability, a decrease of 509 grams. Okay, but now let's take a look at the dummy variables. Compared to white, mothers, a mother being black is associated with 474 degrees of baby weight. Same thing for race. If the race is other compared to being white, it's associated with, on average, a decrease of 347 grams of baby weight. If the mother is a smoker compared to being non-smoker, the outcome is a decrease of 345 grams in baby weight. Again, the intercept is the average of the baby weight if all of the variables are zeros, and all of them can be zero except for weight, so that value is not very useful here. If we take a look at the R-score, it's now at 24%. So just adding the two variable race and smoke really improved the model goodness of fit in between 15% and 24%. Now granted, it's still low compared to what you usually strive in machine learning model to hit a value above 70%, 80%. In some applications we would like to be 90% and above. Again, this task is not an easy task. There are so many factors that are associated with the birth weight of a baby. But even with some of these variables, we've got a decent enough explanation of baby weight, and very importantly, just understanding how these variables relate to baby weight can actually give us some guidelines of how to promote healthier babies. Obviously here cuts, there's something that mothers can work on: cut smoking, reduce hypertension, so on and so forth.